Okay, welcome back, students. In today's class, we'll continue with the unijunction transistor, UJT. Last week, we would have studied the basic characteristic of this device, and you saw whereby as we increase the emitter voltage, we have the device going through different states, right? So you start with it being fired, going to reaching its peak voltage, and then it goes through negative resistance as the emitter voltage is increased, and then it goes into the saturation state. We would then have looked at a model of this device where you see it is just a simple device consisting of P and N-type material. Right, so with the P-type material being sandwiched by N-type material. So out of that, we're able to model this device using just a simple PN junction diode and two resistors to mimic the resistance we have between the two bases, base 1 and base 2. We then develop equations around that. So in today's class, we're going to look at some applications of this device. Right, so it's a very common device that we use to trigger, in particular, things like the SCRs and the triac. Right, so we will be focusing some attention on one of these applications. Right, we have applications, other applications, like sawtooth generators, simple oscillators, phase control, and timing circuits. Right, so the one that we'll be focusing on in today's class is going to be the relaxation oscillator. Right, so with this type, it produces non-sinusoidal waveforms. All right, so what they're looking at here is a basic circuit configuration for your UJT. Let me just move this out of the way. All right. All right, so you notice we have resistors here, biased R2, R3, and we have a capacitor at this point. In a little while, in the next couple of slides, I'll talk more about the external circuitry on your UJT oscillator, relaxation oscillator. All right, but before moving on, I should point out the kind of waveform that you will observe, right, with this type of configuration. If we look at the output, either be at a B1 or a B2. At B1, you notice we have a positive pulse train. At B2, it's a negative pulse train, so it's basically inverted, as you can see here. Right, so note that depending on which output you're taking, you're going to have a set of positive pulse train or a set of negative pulse train. So be mindful of that. All right, so equation that governs the whole charging of this capacitor that you're seeing right here, or discharge rather, is given by this familiar expression. Right, as you can see here, it will follow an exponential decay, or it charges exponentially. So if we now substitute, well, before doing that, I should look further at the waveform. So based on this waveform, this characteristic equation, right, that we have here for the voltage across our oscillator at any given time, right? So it's just a function of the base to base voltage that we have. That's the interbase voltage into 1 minus the exponent of exponent e to the minus t over the time constant. And this time constant here is just the product of resistor R3 and C1. Right, so what you're seeing here is in this region, let me bring this curve up. So the capacitor charges, as I can see here, in this region, and then discharges in this region. So that is what is happening with the capacitor over time t. If we look at the output, this is where we have the output. Now as this device fire, right, if you notice, it fires at precise points, and that's where you have the pulse being formed. Right? Look at the voltage across R1, so that would be the positive set of pulse that you have. So at this point, when it reaches that voltage that would cause this device to turn on, right? So at this point, you notice the capacitor will charges up to this point, and then what happens, the device is switched on, right? So device switches on, so you have that spike right here, right? So you have that spike, and thereafter, as the capacitor discharges and the voltage, right, at the base not being sufficient to keep it into the conduction state, and then you notice the voltage decreases exponentially, right? So that is what is happening here. Now, when the capacitor discharges, right, a point note considering is when it's equal to the peak voltage, right? So that's when it equals to the peak voltage, that's when it will start to discharge. So we can substitute the peak voltage into the equation here, VC. So let VC equal to VP, right? So that's the peak voltage. How do we find the peak voltage? Last week we would have done quite a number of calculations. Just to refresh your memory, you recall this circuitry, right? So the peak voltage at this point, right? So we have 0.7 volts across the diode in the model, and then we'll have the intrinsic base voltage multiplied by the intrinsic standoff ratio right there. So we can make that substitution, but for the purposes of this calculation, making it simple, we can assume that the voltage up across the diode here is 0, right? So we assume ideal diode. So we will eliminate the 0.7. So what you have here is just the standoff ratio multiplied by the interbase voltage. Okay, so that's what you have. So we basically ignore the voltage drop across the diode, and we can now basically simplify this expression. So we expand this bracket and simplify. So and divide both sides by VBB, right? And try to make time. Let us make time the subject of the formula here. So divide both sides by VBB and just add in and rearranging the expression. It comes to this. Just transposing, very simple. So 1 minus the intrinsic standoff ratio, that would be equal to the exponent of minus t divided by the time constant, right? And that's R3 and the capacitance. Right, so after this, we can just take the natural logarithm of both sides of this expression. Right, so by doing that, this side take natural log, and on this side take the natural log. That's just minus t over the time constant. So we can make t the subject of the formula now. That's very simple, right? Let's move this. So that's equal to time constant multiplied by the natural log 1 minus n, the standoff ratio, sorry. All right, so I think I should fix this, right? I have 1 over 1 minus n right here. Right, it should fix. Let us do you understand why? Because we have the minus here. All right, so let us look at this problem. We have a data sheet for this 2N2646 unijunction transistor, and it gives the intrinsic standoff ratio. That's eta. That's 0.65, and we're told that this capacitor here is 100 nanofarad, and that's used to generate the timing pulses. Calculate the timing resistor required to produce an oscillation frequency of 100 hertz. So basically this time, right, using this expression, right, if we figure out what T is, we can work out the frequency, right? So important to, let me go back here, you see clearly, let me move this. All right, so when this when the capacitor, when it's discharging, right, as you can see, it's a combination of RB1 and R1. Okay, so it's important to note that RB1 and R1, right, when we have this capacitor discharging, right, so that's how the current would flow. Right, so the period here would be the combination of the time constant 1 and the time constant 2. So it's between when the capacitor discharges and charges. So that's the time we're looking for, right, this time. Right, so let's go back to the problem. Right, so we start with what we know. We want this to produce oscillations with frequency 100 hertz, right? So we know that if the frequency is 100 hertz, we can work out the period, right? So that period, 110 that works out to be 10 milliseconds, right? So we can now substitute into the expression, right? And work out our value of R3, right? So if you recall the expression, so that's it. We know what the value of capacitance is, right? We know what the time is, time t, so we can substitute, and we also have the intrinsic standoff ratio, so we can substitute these values, make R3 the subject of the formula, right? So we can do that, and we get a value of R3, 95.23 kilo ohms. Right, very simple. All right, so we can, I think last week I would have pointed out that we can actually use this. I will show you here in speed control circuitry, right? So here we have our this is basically a relaxation oscillator, and we're providing our pulse to our SCR gate here, right? So as you can see, very narrow positive pulses, right? So we didn't take the output from B2 but B1 at this point. Remember, B2, the pulse strain is going to be negative. So by taking it from the base 1, we have a positive pulse and being applied, narrow positive pulse being applied at the gate of our SCR, right? And this narrow positive pulse will trigger our SCR, right? So will now cause current to flow from the anode to the cathode, right? So we have our current here, and our motor will be turned on. And of course, by adjusting the pulse, we're able to change the firing angle, right? If you recall, so this variable resistor here, right? We can vary it and get different values of our speed, right? By just varying this resistor. Is there a question?
Yes, sir. So in a practical sense, the pulse from V1, would it cause the motor to pulse or run straight?
No, it's not pulse. Remember, the idea here is that the gate, we need a narrow positive pulse to switch this this device on, right? So the pulse here is just to turn the SCR on, right? So it is not going to cause it to pulse. Do you follow what I'm saying?
Oh, yes, sir.
Right, it's just to switch it on. So you basically control the average output voltage, right? So that's basically what you're doing. If you recall, let me just bring another page. Let me just do something here to refresh your memory. All right. Let's say we have some voltage here. This is Vm, and this is your time, and we apply pulse. Right? Let us say or a positive pulse here. Now at this point, is at that point that you will have this SCR being triggered. Right, so in the negative part it's removed. Right, so here your firing angle. Right, so this is what is happening. So depending on where this pulse is, right? So remember I told you can change that resistor, a value resistor, and change the pulse, right? So by changing the pulse, right? Where it starts, we can basically change the firing angle, right? So by changing the firing angle, we're able to change the average output voltage, right? If we change this average output voltage, we are able to control the speed of the motor, right? So it's not that it's going to be pulsing. We recall the formula, into 1 plus cosine alpha. So by changing this alpha, right, so it's firing angle alpha, we change this average output voltage. So it's not that it's going to be pulsing. No. Do you follow what I'm saying?
Yes, sir.
Yeah, sure.
Yes.
Based on the diagram, would you would so after the pulse, the SCR conducts for the first half cycle. It would go off
Mm-hmm.
on the negative part of the cycle. You would need to fire it again for the next cycle.
Yeah, right.
Okay, all right, yeah.
Right. So it would be in the next cycle that it um, um, would be fired again, right? Because it is removing the negative half cycle. That's how the SCR works. The triac, however, came on the scene to rectify that. So we can have bidirectional conduction, right? So with a triac, you would have conduction in the negative region as well, right? So I guess maybe what he's asking if this motor is going to be starting and stopping, that kind of pulsating behavior. No, you wouldn't observe that kind of uh, behavior where it is coming on and off, if that's what you're probably thinking. Okay, because as I can see, this is pretty fast, right? So you wouldn't observe this kind of a transition. All right, so there's another question I'm going to ask you to work it. Now that you understand this one, ask you to work this one. Right, I give you a few minutes to work this. All right, so consider the UJT relaxation oscillator shown in this figure. This is it. Assume that the UJT has the following characteristics. By the way, these characteristics, you can get them from the data sheet for this device, right? It will tell you if you just put in the device number, let's say maybe a Google search of device number and get the data sheet. It will tell you what the intrinsic standoff ratio is, right? It will tell you what the valley voltage is and the interbase resistance, right? And it can tell you what RB1 and RB2. Is there a question? Right, and IP, right, so that's our peak current, and IV, that's our valley current. Right, so your job now is to find what the peak voltage is equal to. Who is asking a question? If somebody asking. Could you go through it? I just joined. Who is this G2? Who is that? Somebody is asking to go back over. Go back over what point? You mean the entire lesson? You will catch up. What's that? Could you please go through it? This question. Oh, the question. All right. No problem. Right. So this is the question, right? And as I was saying, you have the part, right? This UJT transistor 264.6, and it has an intrinsic standoff ratio of 0.65. And the capacitor that we use here is 100 nanofarad. You're asked to calculate the resistor, right? So this R3 is our timing resistor, right? That would enable you to get a frequency of 100 hertz. So we developed an equation earlier on for this kind of relaxation oscillator, right? So based on the information given, we can substitute the time, because since the frequency is 100 hertz, you know the relationship between the time period and the frequency. That's 1 over the frequency. That gives us 10 milliseconds. And now we can substitute in the equation and rearrange the expression to make resistance the subject of the formula, right? So this is the expression for the relaxation oscillator, right? So R3 multiplied by C, right? So this is R3, and this is the capacitance we're making reference to. Right, so this combination gives us a time constant, and it's into natural logarithm of the reciprocal of 1 minus the intrinsic standoff ratio. So substituting those values, right, we can work out what R3 is. So that's pretty much what we did a while ago. And I would have mentioned to you to pay attention to the output that you're taking. So if it is that you want your positive pulses, then you have taken it from B2. If you want negative pulses, you take it, positive pulse B1 and negative pulses B2. Right, so we then look at another application where we use the UJT to fire or to control the speed of this motor, right? So by using this relaxation oscillator, we're able to generate the narrow positive pulse that we so desire, and apply to the gate of our SCR and trigger it. We can change the firing angle by changing the value of resistor here, right? So by changing our firing angle, we are changing the average output voltage, right? And of course, by changing the average output voltage, we're able to control the speed of the motor. Right, so that's what we have done so far. And now, this is a question I'd like you to work out. All right, so maybe you're wondering, should you take this to be ideal? No. You can use the diode, take the diode voltage to be 0.7. So, of course, you want VP, right? You recall I showed that to you earlier on. So your peak voltage, right, that should be equal to your intrinsic standoff ratio times your VBB, right, plus your 0.7. All right, so you can let me know your answer. Of course, the VBB that is not given directly, so you'll have to first figure out what VBB is equal to before you can proceed with this question. So that's the only part where it will perhaps give a challenge. You pretty much understand how this device works. All right, so you recall that this and we look at the model. Our resistor. Right, so this resistor here, R1, this one R2. Right, so this one, once the have sufficient voltage here, and we trigger or we make the UJT fire, then we have a low resistance part here. Right, so the capacitor that's going to be providing your peak voltage, as you recall. Right, so charge is up, and as it reaches VP, it will cause the UJT to trigger, or to fire rather, and then it starts to discharge, right? So your capacitor will start discharging at that peak voltage, and you'll have a current, emitter current flowing through B1 down to R1. Any answers so far? All right, I'll give you a little more time to think about it.
Sure.
Yes.
For the for VBB, um, since we have VBB is the voltage across the two base, the RB1 and the R, but B1 and B2. So
Mm-hmm.
since it is in series with two other resistors, well, one other resistor, we could use voltage divider rule to find VBB.
Yes, yes, yes. Yes. That's exactly what you would need to do now. So as you can see here, we need the voltage VBB. So this voltage, what's the interbase voltage here, right? So you can think of right between here having some kind of resistance, and that would be your RBB,
Yes.
right? So you could imagine right here being your RBB. So you have your R1, your RBB, and your R2, right?
Yeah.
So what is the VBB, right? Just a voltage divider that you're applying there to get VBB, and then substitute it into this expression. You have the intrinsic standard ratio, and it is very simple thereafter to calculate your peak voltage.
Okay.
All right, so let me know what you get for your VBB.
All right. So basically, so it would be RBB times VS divided by the two resistors combined. So that would be 570 plus RBB. And
Yes,
that give
right.
that give us 23.62.
23.
Yeah,
Okay.
23.62.
All right. I think maybe I calculated it wrong. All right. Uh-huh. All right, but about that, and so what is the VP? So you just substitute now?
Right. So it would
Right.
be in what's that letter again, sir? A Greek letter?
And the intrinsic standard ratio.
No, what's the name of the letter, sir?
Oh, that's eta.
Eta. Okay.
Yes.
So it's eta times VBB plus 0.7.
All right. So this, we say, let me just correct this. This is 23, you said?
Yes, sir.
And what this came out to be equal to?
Hold on. 62 times 0. 16.05.
right? All right, so very good. Very good. All right.
Yes, sir.
So, who was this? All right, so the next part, you're asked to calculate the output frequency. Again, that is very simple. You know how to get your frequency, right, from that expression. Right, you know that R3, right, times your value of capacitance, right, times the natural logarithm, right, into 1 over 1 minus beta, that's equal to t. So if you're able to find the period, then you can find the frequency.
Sir,
Hmm?
is that R3, R3C, LN?
If it's what?
R3.
Right. Remember, I said R3 is this resistor, right? We know. So this is the resistor talking about. So maybe I probably write the RE right there so that you can see exactly which resistor, right? So that resistor.
Yes.
Sir,
Yes.
I'm looking back at the VP that I calculated.
Yeah,
Um,
yeah.
the VBP. I
1493.
something wrong.
Yeah.
The VP.
Yeah, I think we did something wrong, you know.
So
Yeah.
it's hold on.
For the VBB, sir, it's
Yes.
it's it's RBB over the RBB times VS over,
Yes.
which is over 570 plus RBB, right?
That's correct.
When I do that,
98 ohm.
I actually I do it over because I think I had the 570 at the top in the first place.
Mm-hmm.
So
No,
it will be
The RBB here is 9.2 kilo.
9.2. So when
Yes.
I do it over, I get 0.38.
What?
Yeah. So it'll be 24 times.
All right.
It'll be
RBB, right? Uh, what did we say that is RBB? All right. Yeah. This will be RBB. And your RBB here is 9.2,
right.
right? And that's kilo ohm divided by your R1, and your R1 was 5.8.
Oh right. Oh, that's not kilo. Oh, the
5.8 kilo
is
ohm.
not. It was ohms. It's not kilo ohms, no, it's ohms
No, it's kilo ohm.
for the hold on.
That's what
RB1.
is there, right?
Okay, right.
RB1 5.8 kilo ohm and RB2 3.4 kilo ohm. Right?
I
So
think
we
the first
can
value is right.
plus 3.4K, right? And we need to that. So this is RB1, RB2, and plus RBB. That's plus 9.2K.
Yeah, I had the page before.
And we multiply by, and this is 24, right? Or VS is 24, right? So you can put that in your calculator, right? So 9.2 divided by,
Wait. I think we have, sir, R1 is supposed to be, it's not RB1, it's R1 we need an R2. So it would be the 470 and the 100.
I put something in wrong.
Yes,
Yes,
sir.
sir. For R1 and R2, 100 and 470.
Oh, sorry. Oh boy, sorry. The R1 and R2.
I was doing a similar thing, sir. I think the first value is right, the 22 point, it's 22 point, yeah, it's 22.6.
It's 20.
The first value is right, sir. I was mixing up those values also.
470 plus 100.
100.
Right. So please don't make that error. The don't, that's a very serious error. Right.
So it worked out to be 22.6.
Right. So the 22.6 was correct.
Yes, sir.
Okay. So let me put back my value in there.
You had
uh, all right. Where is it? I know sometimes. So 22.6. And what this is,
Uh,
I think it was
14.938.
14 point.
938. Or 94. Yes, sir.
All right.
no, but me get 15.39.
What?
Why, so I get that.
I think we had
Remember, sir,
15.39 there before. Right. I think we had that there before.
that's right,
Um,
answer.
remember, this is 22.6.
What is N? What is eta?
0.63.
Oh, but sir, I have 0.65 right there. You know.
Yeah, that's true, yeah,
Oh,
sir.
0.63. Oh,
Yes,
okay.
sir.
I made an error. Right. So 0.63. Right. So
Yes,
this is an error here.
yes,
0.63. So it comes to 14.94.
yes, sir.
All right. All right. So you can work out T Right, so you just substitute. You know what this resistor is? It's this one, the value of capacitance here, and you know what the intrinsic standoff ratio is? 0.63.
I got 2 minutes.
Huh?
I got 2 milliseconds.
2 milliseconds. Nice. I think maybe my answer may be wrong. So what's your frequency?
500 hertz.
Okay, well, that's probably that's correct, because I think maybe I put in the wrong value. So, but I got 476 hertz. So, but yeah, so you have done pretty much the correct thing. Right. So we could have rearranged the expression and just substitute the values right here. So that's what we need to do. Just take the reciprocal. I will notice this part is now in the denominator, because I took the reciprocal of the time so that I can get frequency. So I substitute RE, 10 kilo ohm, and our value of capacitance, 0.2 microfarad, and 1 over 1 minus, I think I put in 0.65, and that's why I'm getting this.
Sir, I got 502.89.
Wait, what is going on here?
Sir, I got 518. 518.
Let me tell you what you're substituting. Right, so RE here is 10K,
10 kilo ohms. Right, sir.
right? And the CE here is 0.2 microfarad.
Micro. 10 to the minus 6.
Right? And you take the natural log of 1
Over 1
1 over 1 minus
minus
0.63.
63. Yes, sir. It's 502.89.
Yes, sir. 502.8.
How much? 502. All right, let me just correct this one. So that's 503 hertz. So you have another part to do. All right. So now this value of resistance, you have to prove now that the 10 kilo ohm resistance that you have here, this value of resistance, is within the acceptable range of the maximum and minimum resistance that you can have. So in selecting this R, right? So this is a very important point when you're using this UJT. So when you see this value, RB1 and the RB2, right? It's not these two resistors that we were looking at. This is not it, right? It's resistance in the device. Remember when we look at the model, right? This is a resistance in the device, the RB1 and the RB2. From that, you can determine the maximum and the minimum resistance that you can put here. So basically, you'll be able to determine a range of frequency right, that you could possibly obtain from this particular device, right? So you have to use this device, but pay attention to the manufacturer's data sheet. All right, so how you will calculate your minimum resistance, how you will determine the maximum resistance, right? So that's going to be your task. It is very simple, right? Think about it. All right. Go back to, I think I showed you a curve there earlier on, right? This. When, at what point would you have your maximum resistance? Is it at the peak or at the valley point?
A valid point.
I say
Right?
peak.
Peak.
Yes, sir.
Right. So at the the peak, we get our maximum, right? This is where we have maximum resistance, and at minimum, the valley point, that's where we get the minimum resistance. Because you remember, after it fires, then you have that inverse resistance, right? This is where, so this is where you have the small resistance right here, right? So when you look at the manufacturer's data sheet, they tell you, okay, the peak current is 5 microampere and the valley current is 3.5 milliampere. Now, look at the circuit and apply your knowledge of circuit theory, and you'll be able to work out the minimum resistance. It is very simple. Maybe you can look at the model and you can probably figure it out.
Alright, so um,
Yes.
we can go back to the graph that you just showed us.
Yes. So you want that IE, right? So the IE, right? So if you look at it, how would you determine this peak resistance and
Alright,
this?
so that max resistance is occurring at it's at IP right here, and I say IP and VP. So
Right, right,
what I
right.
would do is we have a source voltage. I would, based on the circuit,
Mm-hmm.
if I want the resistance there, I would say it's the source voltage minus the VP, and since this IP, the peak is at IP, I would divide it by IP.
Yeah, that's true.
So VS
Wait.
minus VP.
Oh, it's Conroy. Oh,
Yes, sir.
okay. I was wondering who figured this out. Oh, sorry. All right. Yeah, yes, you're right. Yes, continue. You're right.
Alright.
Mm-hmm.
Alright, go back to the current slide now, sir.
Yeah, which slide?
The current one, the question.
The question. All right.
Alright. So it will be the 24 minus the VP that we calculated over I.
Yes. Right. Right.
That's for the max.
Right. Everybody following?
No, so you can go back again.
All right. Tell them again what how you're going to calculate your max resistance. Right. So he was looking at the graph. So tell them again.
Alright, so the max distance, if you look at the graph, you see peaks right at IP, right? And VP. So if we have it peaking at VP and IP, and we have our source voltage, right? Because the resistor is actually between VS and VP, you know. So if we want to calculate the resistance, it will be VS minus VP over the current that is flowing, which is IP.
I don't think they follow. Do you follow, class?
Yeah, yeah.
All right. So tell them how you get the minimum now.
Alright, so the minimum is actually right above IV, the value point. So uh the voltage at the value point is VV.
Yes.
So I would say it's the same VS minus the value point voltage divided by the value point current.
Very good. Very good. Yes. That's all. That is all. All right. So and do that. Let me know what you get. Mine.
So you get 1.8 for the max.
I think 1.8.
Yes, sir.
Was this correct? The 15.39? I don't remember if I changed the
It was,
VP.
yes, sir. It was saying 14.94, I think.
Okay, 14.9. Let me just change this. So this should be 14 point how much?
I think it was 94. 14.94.
this would make it 1 point,
Eight.
how much?
1.8.
1.8?
Yes, sir.
1.8. All right, good. Right? And you do the same thing. So the value, right? You can look, what did they say this value?
The value current was 3.5 milliamps.
Okay, 3.5 milliampere. All right. And the valley voltage, is that right?
Yes, sir.
Like 1.5.
Right. So
All
we
right.
get the 6.4.
All right. So, all right, you should get that value. All right. So these kind of questions, I really can't get any more challenging than this. So these are the key points that you should pay attention to when you're using this. Somebody asking a question. Let me just check before. Jay Gibson. What 5? Oh, I don't know. All right. So key point. You need to pay attention to the manufacturer's data sheet so that you can select your components properly. As you can see here, you couldn't just arbitrarily place a value of resistor here for a particular frequency, right? You'll not get it within the range, right? So it's very important you pay attention to the manufacturer's data sheet and do your calculations accordingly. Also, the voltage that you'll be using, right? So very important. It's a very good device that we can use to provide pulse, right? And commonly using applications where you need to trigger your SCR, trigger your track, right? So we basically can use it to control the speed of like motor. We could also use it for um, purposes, right? So it's quite useful, right? So